So, hello everyone. Welcome to the intro to ML for robotics. It's actually AI for robotics, not ML. It was always an error with the naming of this section, but who cares? Yeah, and today we're gonna speak about simulation and reinforcement learning. Like with this shortening thing called RL, people sometimes mean robot learning, but reinforcement learning and robot learning is two different things. Yeah, so be aware of that. And today we're gonna dive into basics of those two topics. I'm gonna give you some basic definitions, how they work, and further on we're gonna develop and build something, and I'm gonna show you more examples, I'm gonna dive deeper also. But before starting, I'm gonna talk about purpose and goal of this section. I thought for a while about it, and I decided that the goal is to encourage people. Of course, it's the first goal before starting was gather people who are interested in the same topic, it's robotics and AI, but also goal for the section as for you, as for listeners, as for people who want to learn, is that you will just learn the basics and some basic definition from where you can, like maybe there will be something that you will be interested in and you will be able to study it by yourself at home, and this is just kind of way to give you the touch with robotics and AI, so you know what to learn and learn what things you like to do in robotics or AI or AI, whatever. So yeah, just wanted to clarify that. Today's meeting is not gonna be long because I have some meeting in 1 hour actually, so I'm gonna try to be really quick, and yeah, so let's get started. Starting from the purpose and problems we solve. So there are two different kind of robotics actually, like industrial robotics, and there are old and new ways of building intelligent robots is via predefined rules, if else, and some flexible robots. I'm gonna show you some simple example here, and you're gonna try to guess just from the video which one is predefined and which one are flexible robots. Predefined, hard-coded, same thing. Okay, and second. It's not the better representation actually, but yeah, okay. Okay, I think it's enough. So, what do you think? Which one is predefined robotics, just hard-coded, and which one is flexible robot, which can, depending on the environment, they can decide what they do?
The first one was probably predefined, I guess. And the second one have to choose from some object, so that will be a
Okay.
flexible one.
Someone thinks the other way? Okay, everyone agrees. Yeah, that's completely true. And yeah, that's actually the problem of those factory robots. That, for example, we have a Volkswagen factory here, and the thing about them is when some detail comes to the robot, it knows exactly by the millimeter of um, the position of the detail that's upcoming to the robot, and it knows how it grabs that and how it moves that. So it's like completely predefined movements, like grab something, put something somewhere, and that's it. Like it never thinks; it just makes same movements every time. So um, that's simply it. So, but the flexible robots, like those shown in No Magic, they choose those grippers depending on the datum that is going by the line, by this line. So they have some like different kind of grippers which the model decides. So they are AI generated, and as I mentioned, that's kind of the best, I think, company that does robotics today. I mean, the most developed, the most interesting to follow. So yeah, and those new way of robotics also there's also a part of VLA there, which we discussed before, and also the part of reinforcement learning with the robots, which we're gonna focus today on. So our goal is to make robot adaptable and learnable. I'm gonna read those two things that I found on the internet. One is pretty academic, this one, and this one is simpler. So the idea behind reinforcement learning is that an agent, an AI, will learn from the environment by interacting with it through trial and error and receiving rewards, negative or positive, as feedbacks for performing actions. Reinforcement, and the second one, more academic, more straightforward. Reinforcement learning is a framework for solving control tasks, also called decision problems, by building agents that learn from the environment by interacting with it through trial and error and receiving rewards, positive or negative, as a unique feedback. Well, I'm gonna speak about everything here. Just imagine a dog that you want to train to do something. For example, you have a dog. You say like sit, and if it makes the right decision, you give him a reward, negative or like it's generally positive. You don't kick the dog when it doesn't do your expected thing that you want to do. But I mean that would work probably, and we do that for robots. But I mean, yeah. So this is basically the loop that describes the reinforcement learning. We have some words here, some definitions, some which I'm gonna try to explain to you today. So let's get started. This is a simple example of some game. So think of an agent as our robot, as our human, as our, I don't know, whoever does the actions. Action is basically the action it takes. So, okay, let's move here. Better. So action is some action that the agent performs, and then environment is basically the environment of the agent in which he takes some actions. Also, there is a definition of a state in which the agent doing an action is in environment. So, for example, you have some state here. If he would be here, he would probably try to jump or do something else. So there would be a different function, which different policy. I'm going to speak about policy later in a minute. So, and some reward that the environment gives us after we take some actions. It could be good reward, it could be bad reward. If we do some expected actions, we give a good reward. Like the reward here are numbers. for the model, for the agent to be clear. Okay, so let's move on. Speaking of observation space, there are two type of observation spaces: the complete description or partial description. Most of the time, while working on robotics, we are probably gonna be limited by our camera view. So it's probably which space? If we are limited by our camera view, which kind of observation space is it complete the description of the space we are in, the whole world, or it's some partial description of the state we are in? Yeah, of course. And there's also an action space. It could be a in robotics it's pretty important thing to know. So it's a set of all possible actions in an environment. So it's there are some discrete action space. So for example, we can go forward, we can go backwards, left or right, or for example, as the car driving in the car driving, I don't know, assistance, not assistance, but self-driving cars probably. Yeah, that's most. Yeah, that's right. There are actually the infinite number of possible actions, and that's why we want to learn on simulation, and the simulation is very important thing in taking some actions, because I mean we could have drive a car in the real world and say, oh, well, what if we turn left right here at the road, like we might kill someone, so that's not the best option actually. Sometimes that thing might happen, of course, when we deploy our some autonomous vehicle model, but they are pretty good trained, I think. I mean, I didn't saw any Tesla or Waymo doing some weird things like crashing into people, so they're probably good thought. I mean, they should be. And also we are speaking about reward here. Speaking of reward, it's the only feedback to the agent we give. Thanks to the reward, our agent knows if the action was taken good or not. So that's the basic formula. We have some discount rate actually is I think we will dive deeper about it in the further examples next meetings, because it's not that straightforward. For me, maybe someone knows what that is. Maybe someone learned reinforcement learning. Maybe someone knows what gamma distribution rate states here.
Yeah, so I think it lowers like value of future rewards. So the agent takes. So we have to balance like global outcome and local.
Yeah,
let's say,
that's right.
Outcome. So yeah.
I want to give some example, like, but there was a good picture of the example, but I didn't include it here. So, okay, so we are just balancing between the risk and the output that we can get. So, and this discount rate is just defines this relation, this discount rate. Okay, we're gonna speak about it further on. Don't worry about it if you don't understand, because I'm also not that familiar with that same way. So there are type of tasks, some different type of tasks, episodic and continuing. Starting point, the episodic is starting point at the end point. For example, we have like some game, and we have the starting point where we start doing something, and we have some ending point. That's actually the thing that we do in robotics. We have the episodic task. We start from some certain position. Not always, but most of the time we have the same ending point, which we want to achieve. So yeah, that's like a terminal state, and there are of course like continuing type of task, so that they basically continue forever. There's no terminal state. Yeah. So that's actually the example that could be given about this comrade, but okay. The exploitation trade-off is basically kind of relates with this discount rate I spoke before. So exploration is exploring the environment by trying random actions in order to find more information about the environment, and exploitation is exploiting known information to maximize the reward. For example, there are some mouse in some environment, and it knows if it goes to the left it gets one cheese, if it goes up it gets second cheese, but he knows by maybe some trial that there are some like I don't know, some cats, I don't know, some things that will kill him, so he will not be able to continue. But there's also 3 cheeses, not one. So the reward the reward is basically bigger if we go that way, but at the same time it's more risky to go that way. So basically here we, in our reward function, we define how risky, how risky we want to be in our decision making. So, and if a mouse found some good way of, for example, taking these 3 cheeses in very like easily without a risk, and it's basically doing the exploitation. It just makes the same movements. If we put a mouse here, it would go here and just take our cheeses, and because it knows if it goes that way, it's safe and it's good, but it goes that way, it will be not safe, and the exploration part is missing. And we define this by our the discount rate here. And also, I didn't speak of those why we have some few rewards here, because we have few rewards. Think of it just like yeah, here's a good example. We just take the sum of all the, for each action we have 1 reward for. So think of it like maybe in every frame our agent is doing some action, so in every frame we will have some reward function summing up with our discount rate. So we just sum. So basically those rewards are for 1 frame each. Yeah, that's it. Yeah, so the simpler example for exploration trade-off. Imagine if you have a shop that's opened like for a few years, I don't know, 10 years more or whatever, and you usually go there when you want to eat. And the thing is, when there are new place opening behind it, near it, and you start to question yourself, maybe I want to try something different, but I don't know if the food will be good. So, and that's also a very important thing in our reinforcement learning, to like define this, try to define this discount rate to decide, well, where we want to go. Would we like to risk, but we might get the higher value of food, or we would go to the usual place and do the same things we did before, but we will not learn anything new, but we will have a good experience at the same time. Okay. Yeah, and this is some summing up of what I said. So exploration is trying random actions in order to find more information about the environment. And exploitation, using information to maximize the reward. I'm gonna try to do something on my laptop in a minute, because I want to set up some environment from NVIDIA which takes usually so long, so I want to do that beforehand. 1 second. Okay, it's deploying. Cool. So, is it understandable? It should be. Okay. Just giving you some basics. There might be boring. I found them boring, but what can we do? We need to start from ground zero for everyone. Yeah. So the policy is the brain of our, which I mentioned a minute ago. It's basically the brain of our robot. So the policy is the brain of our agent. It's the function that tells us what action to take given the state we are in. So it defines the agent's behavior at a given time. So training reinforcement learning model is just training policy, defining a function, which can take some argument, which is our state, and based on that state, we can do some actions. Simple as that. Okay. So there are some policy, and of course we have some. Okay, not right now. So it's basically the function. It's simple as that. So policy-based method can be deterministic. A policy at given state will always return the same action. Yeah, that's also a very important thing. Given that we are at the same state in our environment, our policy can take same action as it was taking always, as it trained to take once, and it's just taking the same action every time. But there also can be a probabilistically the distributions over actions. So at the same state, we can have some probabilities. Oh, if I go that way, that would be better. Or there's also a way of going somewhere else, which is also not that bad. So we have this kind of distribution with probabilities. Yeah, simple as that, I think. Yeah, that's probably understandable, I hope. So, joints of the robot. So here I found some dog-looking robot. Those are our learnable parameters, which define motion in certain states. So think of these joints, because I think you know that in every joint that I showed here with the J letter, they are just a motor, and the movement of the robot is defined by only rotation of some motors basically, and a good when we walk, when we do anything else, when we move, it's basically the rotation of our joints, like one joint, second joint, third joint, and so on. So when we train a robot, we train those movements of the robot. So our joints are basically the parameters that we try to learn, and those are basically the actions we take while trying to learn. So yeah, I think that's.
Meet my friend.
Oops. Yeah, that's it for the introduction. It was just brief. We briefly discussed about some topics and some definitions. No, we discussed about one topic, the reinforcement learning, but we only discussed some definitions. I think it's understandable right now. So I just found some video, summarizing our presentation.
Meet my friend. He's a robot learning to walk. He knows nothing at all. Perfect. That's reinforcement learning. He tries actions.
Okay, one.
Meet my friend. He's a robot learning to walk. He knows nothing at all. Perfect. That's reinforcement learning. He tries actions. Good actions get rewards. Bad ones, penalties. Reinforcement learning is trial and error, but math. He has a policy. That's how you rate in choosing actions. At first, trash. Every move updates that policy. Good moves get reinforced. Bad moves, deleted. He's using grading ascent, climbing towards better actions. Now he learns a value function. He learns which actions pay off later. More balance, less chaos. Look at that. Progress. Wait, not that way. And that's why reward design matters. Unless you want a robot that walks directly into nature. And that's why you should.
Yeah. Quick summing up. So, speaking of. Okay, it's ready here. Speaking of robots and how much time do I have? Huh? Yeah. I have to do those things in order to. Okay, so I'm gonna try to show entire screen. Oh my god. Okay, it could be worse. So what are we doing here? Okay, it's not ready. Here is some NVIDIA environment to run some ISAC sim. They provide some development environment to run some simulations. Being honest, I was not capable of running it before starting this lecture. Today I just hope it will work, because yesterday, I don't know, some problems with servers or whatever, I couldn't. So getting back to our presentation, because I just wanted to show you that. We need to, speaking of simulation, before doing some simulation of a robot, we need to define our robot. We define it by the format called URDF. It's basically a format that describes our robot. I'm gonna show it in 1 second here. So those yellow lines describe two relative objects. For example, if this object moves toward from the side of this object, for example, if it moves like that, it's dependent on that axis. So it's basically a joint. So the joint is if there are two elements and they are dependent on each other and they move in some way. So for example, if we have a knee, it's dependent on those two parts. That's why we have some kind of movement. The same thing here. Think of it like, I'm gonna show this in the simulation. So think of it like a robotic camera holder. This is the camera. It can be simply removed, or because yeah, it's dependent on this joint, on this axis of our this thing, this stick, and they're all dependent. That's why they're like on each other. That's why they are shown with that kind of yellow arrow. So yeah, basically like that. And each of them have some axis, which which gives the relation in the space. But all of that in example. So we have some base, slider, arm, and camera, which are shown here. So there are some common joint types. We can revolve something, we can move something. It's the prismatic thing. It just moves left or backwards, or down and up. The continuous one is when we move something continuously, like spinning wheel or something, and fixed, just it doesn't move. Basically, and we have some link. Link is that this thing, for example, the arm can be a link. So the arm joint is gonna be this one. So for example, the arm joint has the hand link and the arm link. So two links, they make some joint, because every joint consists of two links. As I told before, this is how it looks like. This is the code, our description, how it looks like, how it's defined. I'm gonna show you a better example here. Yeah, demo part in simulation. That's where we. So I ran on Ubuntu because that's the best way to run it. I use ROS2 to run all that things because it's only compatible with ROS, and most of the things you do in robotics you do in simulation. No, you do in ROS, not simulation. I mean, yeah, kind of same thing, whatever. No, not the same thing. So we define some Xacro. Xacro is basically some additional instrument in our URDF file format. It can be without Xacro, as I show here, but it actually depends because it just gives us some additional functionality to our URDF file. We can define some parameters and so on. So what I've defined here, there is some base joint, which we define some origin, some no. Okay. The green thing is the base, and we have defined the origin, but basically the axis that I showed before. And we have defined the position of the origin in our space. We have defined the parent link world and some child link, which is the base link, which is this part, the blue part. I think, I hope it should be like that. So the next thing, so it's basically a XML file that it's pretty straightforward to understand. So we have some link name, we have some origin of it, we have some definition of our geometry. It's just a box with a size of 2.5 meters, x, y, z, 2.5 meters, 1.5 meters, and 0.1 meters, and so on. We define the material. Green, it's not the material you can think of, like I don't know, some plastic or whatever. It's in this simulation, it's basically the color. So we can distinguish some parts, and we can also define some collisions, some collision borders of some parts, so they don't collide with any other objects. I think me explaining it here, it's not really the best way for you to learn it. You can always learn it by reading it by yourself. I'm gonna try to not forget to send you those information in the Discord, because last time I forgot to send. I don't know if some of you care or not, but yeah, I forgot to send the Colab notebook. Okay, whatever. So it's basically the definition defining our simulation. And this robot, this very simple robot, can be given to can be uploaded to the Isaac Sim simulation, and we can run some reinforcement learning on it. I would like to show you, but I'm not sure if it's gonna work this time. I mean, let's hope. I really encourage you to learn about the URDF file by yourself, because it's basically like definition of the oh no. Definition of the robot. Okay, the quick start is described right here. So, making a new terminal. Right. Okay, as always, we need to. So it should work if I do something like this, but it doesn't. Okay, same problem. I mean, in theory they say it will work. It's kind of new thing by NVIDIA, but it doesn't work. I mean, I don't know what to do, because to run this kind of simulation we need some very expensive things that cost $3.6 per hour to work on, to just launch, and unfortunately it doesn't work. Like, what can I say? I would like to say that I'm sorry, but I'm not sorry, because they're stupid. I don't know what to say. And they don't have any kind of support. I tried to launch it yesterday for like 2 days, for 2 hours, 3 hours. I don't know what was that, but it was quite hard to wrap my mind about it, and I couldn't. So that's it for today. we spoke about the most important things about robotics and simulation. Do you have any questions? Okay, so the next week I'm not gonna be able to give the lecture because I'm gonna be in Germany, and hopefully the next meeting will be in 2 weeks. I'm gonna write that to the group also. Yeah, I think that's it. Thank you for your attention.
Kiedy do tej sali zginie, to